All right, it's a pleasure to welcome Lin Lin from UC Berkeley, who will tell us about dissipative preparation of ground and thermal states.
Thank you. First, I'd like to thank the organizers for inviting me. This is joint work with Zhiyan Ding, who's a new assistant professor at the University of Michigan, Yuntao Zhan, who's a grad student at Caltech, and also John Presco. And this is a work in preparation. Hopefully, it will be on archive in a few days. So the importance of a ground state preparation doesn't need to be emphasized to this audience. So we know that for some strongly correlated quantum chemistry problems and also strongly correlated quantum physics problems, we're very interested in preparing the ground state. Even we're interested in, for example, the high temperature superconducting properties of cuprates. The parent state, which is the zero temperature, is still quite important. So the prevailing way for preparing the ground state is quantum phase estimation. There are numerous variants of it. Let's call them post-QPE-based methods. All of them fundamentally work in a way that is like filtering or post-selection. What I mean is that you have some initial state called a phi, and we do an eigen decomposition in terms of the eigenstates of the Hamiltonian called psi I. Then we look at the population resolved to each eigenstate. We need to make an assumption that it is a P0, which is the overlap between the initial state and the target ground state is non-zero. Actually, needs to be significantly large for this to work. The rest of the states, sometimes it can have overlap with first excited, sometimes overlap with second excited states. Those are OK. Then we run a quantum algorithm to perform an approximate filtering step. What it means is that it filters out the unwanted contributions from other states and pretty much only keep the state you want, which is the ground state. So in the end, you need to repeat this process to really see the target state, because you might also get garbage. The number of Monte Carlo repetitions is about 1 over P0, the inverse of the initial overlap. And you can improve this to the optimal scaling, that is P0 to the -1/2. But for general problems, we cannot expect to improve beyond this scaling. And this provably fails when the initial state has 0 overlap with the ground state. And so one interesting question is whether it is possible to achieve efficient preparation of the ground state from arbitrarily small P0, including P0 equals to 0, at least for some Hamiltonians. And this is one of the questions we're going to answer. The second one is thermal state preparation, or Gibbs state preparation. So again, QPE is one of the earliest methods to do this, but it has been superseded by post-QPE type of methods such as QSVT and many others. So we're given, again, a Hamiltonian, and we want to prepare the normalized thermal state, which is a mixed state, e to the minus beta h, and where z beta is the partition function. So one way to do this is to prepare the so-called purified thermal state. What we do here is to start from the maximally mixed state and apply e to the minus beta h on the second register, and then do a partial trace. And this will give us the desired state sigma beta. So the cost of this is roughly square root of n, and is the Hilbert space dimension. So over z beta, what it means is when the partition function is approximately the Hilbert space dimension, which is the case when the temperature is very high, then this procedure is pretty efficient. But when the temperature is low, z beta is usually much, much smaller than the Hilbert space dimension. So the cost of this algorithm will be provably high. It actually doesn't distinguish very much between the worst case scenario and the average case scenario either. So if you're given the physical Hamiltonian, this is from transfer field Ising model or some other systems, it just doesn't care. It pretty much only cares about the temperature. So this often means that such a procedure is only efficient at a very high temperature, where beta inverse is poly log n. So this is very, very high temperature, because usually when we say high temperature, we're talking about a fixed constant temperature. And this is really depends on the system size. So a question that we're interested in is whether it is possible to achieve efficient preparation of thermostates at some constant temperature beta, at least for some Hamiltonians. So the commonality of two questions is I'm not trying to design a quantum algorithms that works for all Hamiltonians, because there are many, many well-known no-go cases, and either NP hard or QMA hard. So the common thread for designing algorithm is dissipative dynamics. We have heard this term a number of times in this conference already. And this subfield has received a lot of interest in the past few years. But it has a really much longer history. And the idea is very simple. We, instead of a closed system, just considering the Hamiltonian H, we're also considering environment and consider the coupling between the system and the environment. Then the interaction between the system and the environment or the bath naturally introduces dissipation. What is a bit new in the past few years is we seriously consider the possibility of treating this not as a physical model and design approximations to the physical model, but really view this as an algorithm. This is very much like the case in classical Monte Carlo dynamics. We design processes that may mimic nature, maybe not mimic nature, like a replica exchange or other things that the nature doesn't do. But if we design these algorithmic processes, and the efficiency can be even higher than that of the processes happening in nature. So there's a natural quantum analog for enabling such a design. So specifically, the so-called Lin dynamics plays a fundamental role in designing such continuous time algorithmic protocols. When we consider discretization, things become a little bit different. But in the continuous regime, Lin dynamics does become a very natural candidate for designing such algorithms. And the way how these algorithms work is also can be quite different compared to the standard coherent circuit-based quantum state preparation. So coherent, or let's say even adiabatic state preparation, we start from some very well-defined initial state and just evolve the system, and according to, for example, some Hamiltonians. And in the end, we do some merriment. And we can only hope that the target state, whether it's ground state or thermal state, can be prepared starting from this well-defined initial state. Let's say I just talked about the thermal state preparation. We're starting from the maximally mixed state. We apply this e to the minus beta h over 2 to the second register and trace out. We get the target state. So this dissipative state preparation works in a fundamentally different way because we're trying to encode the target state as the fixed point of the dynamics. So what does it mean? It means that fixed point is I just keep applying this dynamics, which can be viewed as a quantum channel, and that depends on simulation time t. As t becomes sufficiently large, they will all converge to the same state. It doesn't matter whether you start from all 0, or whether you start from some maximum mixed state, or starting from somewhere else. Of course, if you start from somewhere that is closer, you will converge a little bit faster. But the hope is that we can design this dynamics so that it really prepares the target state starting from anywhere. And that gives some intrinsic robustness to this kind of protocols. So the unified theme that came out in the past few years really takes a relatively simple form. If this is the first time you see it, it might seem like a lot of terms, but really these are the common ingredients of all these algorithms, including the things I'm going to talk about today, and also done by many other researchers in the field. So we consider the following continuous time dynamics, d rho dt, and which has 3 terms. The first one, G, is a Hermitian matrix, which is called a coherent term. It can be as simple as the Hamiltonian. The second term is the most non-trivial one, the k rho k dagger. That's called a transition term, where k is called a jump operator. And the third term is k dagger ka, and that is called the dissipation term. And AB, this just means anti-commutation. This jump operator is not something that is arbitrary, but actually takes a very, very specific form. So how it works is we pick some simple operator called A. Some people call it coupling matrix or coupling operator. These things do not need to have any explicit knowledge about the system Hamiltonian, can be very agnostic to the specific systems of interest. And then Heisenberg evolved such kind of coupling operators A. So e to the IHS, A e to the minus IHS. So this H encodes the information of the system you're interested in. And then we average them with respect to a filter called F and integrate from minus infinity to infinity. So integration from minus infinity to infinity may sound a little bit scary, but if I just make F to be compactly supported, then this again means that finite simulation time. So the coherent Hamiltonian is constructed from, again, information only from the Hamiltonian and the Ka. So the protocols really, you can see that this gives you a finite design space for dissipative engineering. It's very, very different from VQE, the variational solver. You give me, all these different gates and just play with them, tune parameters, and variationally tune and see whether you can reduce the loss. This is completely different. It's a slightly larger design space than QPE, but not infinitely large. Within this framework, there are actually only 3 things that can be tuned. First is the choice of the coupling operator. 2, the choice of the filter function. 3, the choice of the coherent term. There are no other things that can be tuned. There's nothing that will be variationally tuned. Once you have designed the protocol, then you can just run it without tuning any variational parameter, but these parameters themselves should be aware of the information of the system you are interested in. So give you some examples how this works. Again, these are toy examples, but you can just verify with a pencil and paper and see that how this works. So these are like single qubit examples. Specifically, H is equals to minus Z. So the ground state is 0, 0. So here we choose the coupling operator A to be just the Pauli X. Right? Doesn't necessarily need to know the information of the Hamiltonian, but the jump operator does know the information of the Hamiltonian. I claim that there exists a filter such that you just run this algorithm. It produces a jump operator K, and you can see that it becomes a more it goes from a Pauli X and goes to an annihilation-like operator. And here I just choose the coherent term G to be 0. So why this is a good choice? And because direct calculation shows that for the target ground state, which is a sigma equal to 0, 0, it satisfies that the L acting on this sigma is equal to 0. You can directly verify that. And if you can see K is annihilation operator, that immediately, you can see that it works. So, but does it really, that is a necessary condition for sigma to be a fixed point. Does it really converge from anywhere? The answer is yes, but I'm going to explicitly show that if you start from 1, 1, that has a 0 overlap with the ground state, this thing works. This is because the dynamics has an explicit form. It goes from a diagonal matrix to a diagonal matrix, and you can see that as t goes to infinity, it converges exponentially to the ground state, even though the initial overlap is strictly 0. As a matter of fact, it converges to the ground state exponentially fast, starting from any initial state. And this is also a consequence of the fact that the Lin-Blad dynamics is a trace-preserving map. It's stronger than that. It's a completely positive trace-preserving. Completely positive ensures that at any time t, the density matrix is physical, and trace-preserving means that you never lose success probability. There's never a post-selection process. You just run this dynamics, and in the end, you accept it with a probability 1, and it will be the target state you're interested in. So let's consider again for the same Hamiltonian, but for thermal state preparation. Here I do need, it's the same form, but I have the same single qubit Hamiltonian. Here I'm still choosing the coupling operator to be the Pauli X. Here I claim that there exists a filter F such that after choosing that F and going through this recipe, then I will end up with a K that is 1, 1 e to the minus beta 1. And I also need to choose this coherent term to be some constant times the Pauli Y. And I claim that doesn't come from some sort of like a cheating, that comes from a well-defined algorithmic protocol. And plugging this in, you can directly verify that this dynamics, which looks a little bit non-trivial, but when you apply the L, called the Lin-Bladian or Lin-Blad generator, to this sigma beta, this is equal to 0, satisfies the necessary condition that the sigma beta is a fixed point of the dynamics. Let us again start from the same initial state, 1, 1, which is very, very far away from the thermal state, not zero overlap, but very far away. Then you can do explicit computation, and this is slightly more complicated than the previous one, but you take t goes to infinity, you will see that this again converges to sigma beta exponentially. So again, this is not a coincidence. It converges to the thermal state exponentially fast from any initial state, and there's again no post-selection. And after a certain time, this succeeds with the probability 1, and the trace distance between the target state and the fixed point can be bounded by any given epsilon. So what is the total Hamiltonian simulation for this Lin-Blad-based protocols? The upper bound of this is called a mixing time, which characterizes how long it takes for the system to evolve so that the state is close enough to the steady state, regardless of the initial state. So a mathematical definition of this is that we can use the so-called trace norm, the trace distance, or defined by the trace norm, or so-called Schatten-1 norm, depends on your which community you come from. Let sigma be the stationary state, and the mixing time with some precision parameter eta is given by the minimal time t, so that the trace distance is bounded by eta, started from any initial state. Of course, this is a worst case estimate, and because if you start from some sort of an engineered initial state, the result could be better. So we're also interested in the so-called end-to-end efficiency. So there are a couple of, well, for some physical systems, whether it's a spin or it's a fermion, defined, for example, in sites, there are a few components in the end-to-end efficiency. The first is, can we efficiently construct the Lin-Bladian? This is called CL, the construction cost. The second is, once we have constructed the Lin-Bladian, which means we have the jump operator, we have the coherent term, can we efficiently simulate the Lin-Blad dynamics per unit time? This is the simulation cost, right? So that's the second step. And the third is the T-mix. That's the upper bound for the simulation time. I know the cost per unit time. I also need to know how long I need to simulate the dynamics overall. So the end-to-end cost, roughly speaking, can be said to be CL times CS times T-mix. And only CL is related to the gate complexity, and the others are related to the query complexities. So there's recently wrote an essay on this or a perspective article on this topic. You can please check out. They're very interested. So we're also interested in implementing such kind of dissipative protocols on the device that is as near term as possible. Whether this could be near term, we don't know, but at least we get towards so-called early fault tolerant implementation. But what are some of the considerations for early fault tolerant quantum algorithms? As far as I know, there's no universally accepted definition of early fault-tolerant quantum device. There's some recent discussions on this topic. But roughly speaking, people generally agree that there will be a limited amount of useful quantum resource. And the definition of useful can be different, depends on what kind of architecture you're using. But we may need to selectively apply, judiciously apply quantum error correction and resources to components that are most susceptible to noise. And we sometimes may want to use a hybrid architecture combining analog and digital elements. And there are people working on a technique called a partial error correction, or I think that's very interesting. And there are also, we might need to apply some sort of like a non-fault tolerant error mitigation and error suppression techniques in combination with error correction. So what it means is we need to design significantly simplified algorithm before considering for practical deployment, especially for this relatively complicated dissipative protocols. Of course, simplicity is only a guiding principle. Ultimately, we need to compile everything down to the gate level to really see whether it is early fault tolerant. But at the beginning, at least on the theory, we need some sort of a guiding principle when we design algorithms. So are these existing algorithms close enough to early fault tolerant yet? Well, in the past few years, there have been very efficient high-order quantum simulation of Lin dynamics developed very similar to that parallels the developments of Hamiltonian simulation. And this can go to arbitrarily high order, which is very encouraging, but the protocols are pretty complicated. It's unlikely we're going to implement those algorithms as is on early fault-tolerant quantum computer. But there are also another class of algorithms that have been developed or explored. That's called a weakly repeating interaction or weakly coupled system path interaction models. Roughly speaking, they all look like the same, which is you have some sort of a system evolution, you have some environment evolution, you have some system environment evolution together, and you do go through this a number of protocols. Some people call it flow K type of protocols, and they are the same thing. So you coherently evolve a bunch of things, and then you measure the ancilla. You discard what you get from the ancilla and reset it to the same initial state and keep doing this. And hopefully you will end up with a fixed point. So this is a very powerful protocol and looks reasonably simple, at least has some hope of being implemented on early fault-tolerant quantum devices. But the purpose of this talk is to say that, one of the purposes is to say that details matter. And this is what we want to show. Specifically, well, this table maybe contains too many things. We think that we have like the first work with the mixing time guarantees for physical Hamiltonians in a weakly coupled system path interaction framework. So how much time do I have?
It's another 18 minutes.
18 minutes, sounds good. So this would be like the punchline of this development. So it used to be that the Lin dynamics is considered as after some Born Markov secular approximations, and we end up with an approximation that is called Lin dynamics. That is the older perspective from non-Markovian dynamics. But the recent years, really, the Lin-Blah dynamics provide some new perspectives to the system-bath interaction by providing rigorous mixing time analysis and rigorous performance guarantees. So, really allows us to design more efficient protocols. So let me quickly say like how this ground state preparation and thermal state preparation protocols are designed. For the ground state, as I said, K will be the integral of this Fs times Heisenberg evolution. You can also insert the resolution of identity so that you can resolve them into the term on the right-hand side. So the F, the filter, is designed to only allow energy decrease, but not energy increase. The idea is that you can let F omega to be only supported on the negative half line. Then immediately from the expression of K, we see that the energy, you can only go from side J with the high energy to the low energy, not the other way around. And in the end, what this dynamics does is going to shovel the high energy components to the low energy ones all the way so that the ground state is the only possible fixed point. So this is an example how it works for the TFIM model, which is A to be just a poly X. It is very sparse in the computational basis, but the corresponding jump operator in the energy eigenbasis has a lot more entries, and it is possible to go in the energy eigenbasis from any state connects to the ground state. So there is a explicit construction. Let me just skip that. So is this really protocol really efficient? Here's just one example where we consider the anisotropic Heisenberg model, which is a non-integrable models. We set the coupling operators to be all the poly X, Y, and Z. This is called the bulk cooling. What we find numerically is that the mixing time scales logarithmically with respect to the system size. And Friday morning, Zhiyan and Yongtao are going to give a talk on this topic. And we can also theoretically prove the mixing time is short in this so-called weakly interacting weakly interacting spin systems. Specifically, we consider Hamiltonian, that is the sum of poly Z plus perturbation times epsilon times geometrically local term. Then note that this epsilon is smaller than some epsilon star, but the total perturbation measured by the operator norm is actually large because we can go to the thermodynamic limit. What we can prove is that there exists epsilon star when epsilon is smaller than that, then the mixing time is log n. N is the number of spins in the system. Again, if you're interested, please feel attend the Friday's talk. For thermal state preparation, there has been really tremendous progress on this topic in the past few years. What is most remarkable is the development of efficient and exact detailed balance condition for thermal state preparation. Here, efficient is the key word because one exact one, but inefficient, called the Davis generator, that has been known for decades. So the classical Markov chain, the detailed balance condition is expressed usually in terms of some symmetry conditions. So this one maybe is more well-known to people. But there is a mathematical reformulation that is actually more convenient, but maybe slightly less well-known. That is, we consider some continuous time Markov chain dynamics with the generator L. It's adjoint operator L dagger is symmetric with respect to a sigma inner product. Sigma is the stationary state. So that condition is called detailed balance. So it has been a long opening question in the field, how to design exactly detailed balanced Lin-Blahdian for quantum systems. Finally, in the past few years, people have agreed that this Kubo-Martin-Stringer detailed balance condition is the way to go. It is defined first through an inner product. That is, you have sigma, which is invertible, then we design inner product to be trace, x dagger sigma 1/2, y sigma 1/2. If this is the first time you see it, it does look strange. But if you really allow everything to commute, you will find that this is the same as the classical one. And the KMS detailed balance condition says that the L dagger, the adjoint of the Lindbladian, should be symmetric with respect to this inner product. The importance of this condition is that the L doesn't need to resolve the so-called Bohr frequency. What it means is the filter can be chosen to be decaying very fast as S goes to infinity. That can be truncated, and which implies efficient simulation. So that is one implication of the KMS detailed balance condition. So then there are two KMS detailed balance construction. The first is called the CKG construction by Chen, Castellano, and Gideon. So it uses a continuously parameterized quantum channels by the frequency and k omega. So you have some common filter. Actually has been shown that if this filter needs to be chosen to be real, it must be a Gaussian, which is remarkably strict. So you choose any f weighted by a Fourier mode. If f is real, it must be some sort of a Gaussian to satisfy the KMS DBC. Once you choose this f, then another result is you can prove the coherent term is uniquely determined by this k omega and gamma omega. And so it's really everything's fixed other than some relatively simple like parameter choices. It's really a remarkable paper. So that's called CKG construction. So last year we had our own construction, which is a generalization of CKG in some sense, because it started from like this technical condition that f has to be real. It sounds like extremely technical. I mean, what's the importance for f to be real? But then you realize that f is real means that the energy transition has to be symmetric. It means going up and going down, they're all the same. But cooling is nothing but symmetric. Cooling is going all the way down. And the other way is explicitly penalized. So that means to achieve cooling more efficiently, you have to allow f to be complex. And once you allow f to be complex, you immediately realize that one, you don't need this continuously parameterized jump. A single jump is is enough. Also, its form can be very flexible. And there are infinitely many choices, not just Gaussian, infinitely many choices of jump operators that can all satisfy the KMS detailed balance condition. Once you choose k, then the coherent term is determined by k to satisfy KMS DBC. So the single qubit example I showed earlier comes from explicitly this recipe. And another important thing of the DBC is that it enables mixing time analysis for non-commuting Hamiltonians. The reason is if we choose a short t, means k, if A is local, then k is quasi-local. Then with the Lieb-Robinson bound and the perturbation theory, we can prove the fast mixing or rapid mixing type of results. And this has enabled the mixing time analysis for high temperature non-commuting spin systems and also weakly interacting fermionic systems for all temperatures. So it's a really remarkable progress has been made by the community in the past few years. And many more will likely come in the next few years. So in the final few minutes, let me quickly say something towards early fault tolerant implementation. Let's recall the system bath interaction framework. In fact, this framework has already been used in earlier works, such as the ground state preparation, and where you can use one ancilla, but you use both forward and time reversed Hamiltonian simulation to implement a ground state preparation protocol. The time reversed simulation is not a big deal on a digital computer, but if you were to utilize some of the analog devices, such as neutral atoms, and this doesn't quite work directly. So we wonder whether we can further simplify the protocol to only utilize the forward in time Hamiltonian simulation. It turns out this is possible. So there's a unified algorithm for thermal state and ground state preparation. It uses one ancilla qubit. It is very simple, and the one ancilla implementation is enabled by some sort of randomized choice of the bath and the initial state. So starting from some rho E, which is just acting on a single qubit, and it's a well-defined state, HE is just chosen to be Pauli Z, parameterized by a frequency parameter omega that is randomly chosen within a certain interval that will be specified. Then we consider a system bath interaction parameterized by alpha. Alpha is in interaction strength. And this FT and A are exactly the filter and the coupling operators you have seen previously in the Lin-Bladian description. So the implementation is this. It's just a one line, and this is the algorithm, and the claim is by careful choice of the parameters, it should prepare the ground or thermal state. And you just repeatedly apply this discrete version of the channel. And how it works is because, at least to second order approximation, this can be well captured by an effective Lin-Bladian evolution. So the choice of parameters are HE is just a minus omega 0 or 2. BE is just a 1, 0, so very explicit. Rho E is the thermal state. And if a ground state preparation, that's just a 0, 0. Omega is randomly chosen according to a distribution that allows large energy transitions. And AS is randomly chosen from a user-provided set, not a universal set. If it's a universal set, then this will be provably inefficient. Like you want to choose a much smaller set, but sufficient to guarantee mixing time analysis. And FT, in this case, is chosen to be a Gaussian that is similar to the earlier work by Chen, Castellano, Brandao, and Gideon. We want to prepare this as a fixed point, right, called the rho fix. And the target state, we prove that as alpha goes to 0, sigma goes to infinity, this target state will be exactly equal to rho fix, and the whole protocol is efficient. Specifically, the mixing time for this, because it's a discrete channel, the mixing time is not directly a continuous time thing. It should be a discrete time thing. Let's call it the integer mixing time. That is the number of applications you need so that the target state is close to the fixed point. But because there's alpha parameter, if you do a dimensionality check, you will find that the natural definition of T mixing should be alpha squared, the interaction strength, times the integer mixing time. That's called the T mix. Then what we prove is that for free fermionic systems, the system itself is trivial, but the fact that it can be prepared dissipatively, especially dissipatively by this particular protocol, is actually far from being trivial. The ground state for free fermions is poly n, and there's an absolute dependence. Thermal state for free fermions, there's again poly n times beta and log n over epsilon. And thermal state for commuting local Hamiltonians is again poly n beta log 1 over epsilon. So let me just again use this picture as the conclusion. So before, starting from 60s and the 70s, it is well known that Lin-Blad dynamics is an effective, but far from being perfect description of a non-Markovian system bath interaction Hamiltonian. The idea is that you reverse this thinking. You first design the Lin-Blad dynamics, right? You know that this already works because of the recent progress. And now you ask whether I can engineer a system bath interaction that approximately implements the Lin-Blad, not the other way around. Right? I first know the Lin-Blad works, and now I engineer a system bath interaction that approximates the Lin-Blad that can be efficiently implemented on the early fault-tolerant quantum computer. With this, I'd like to thank you very much for your attention.
Right, questions? Yeah, here. Oh, sorry. Go ahead. You have the mic.
Sure. What makes a state hard to prepare with the Lin-Blad?
Mixing time is very long.
Yeah, so I guess I'm thinking of, in comparison to, say, adiabatic state preparation, where you might have to go through, if you start with some initial state, you might have to go through a phase transition or something. And there's a gap so I can sort of get a sense of why it would be hard to prepare certain states.
So specifically, it would be the Lin blot gap is very small, and you have a lot of states where the Lin blot generator or the Lin blotting acting on those states is close to zero. Those are called the metastable states. Some people call them metastable states. If you have lots of them, then you're in trouble. Okay. But how it works, I would say that there's no natural connection to how adiabatic states work, because adiabatic state preparation starts from some specific initial state, right? And then you go somewhere. The Lin blotting just doesn't care. I mean, sometimes you start from some initial state. I mean, it might help, but when it's a rapid mixing, I mean, it just doesn't care where. But maybe you can say in some hard parameter regimes, it is impossible to prove rapid mixing. That's possible. I think we really don't know nearly as much as we do for adiabatic state preparation.
Yeah, there were two questions over here. Yeah.
Okay. Hey, thanks. I'm a bit confused about last slide, where is alpha, you define, no, sorry, last slide, you defined mixing, scaled mixing time as alpha square.
Yeah.
Can you comment on this, why it's alpha square, and how T-mixing also depends on alpha?
Yeah, sure. Yeah, so because this protocol is a weakly system bath interaction, right? So if I turn alpha equal to 0, I mean, just doesn't do anything, right? So really, alpha, you can think like the Lin blotting appears in the second order expansion of this protocol. The first order vanishes by design. The second order is alpha square, and that's roughly t, or delta t.
But if alpha 0, your mixing time is 0.
Sorry?
If alpha 0 means your mixing time is 0, it's a little bit confusing.
Alpha 0? Okay, can you say?
No, so you say your T mixing is alpha square your number of cycles. So if alpha equals 0, does it mean that T mix is also 0?
Let me see. Oh, no. It should be read in the other way, which is this T mix. You first prove T mix is some number, and tau mix is T mix divided by alpha square. That's the number of applications. Alpha small, you're screwed. Yeah. So,
I see. Interesting.
Yeah, you don't want alpha to be very small.
Thanks.
Yeah.
Okay, one more question right here.
Thanks for the nice talk. I wonder if you can make more comments on the performance of this Lin blotting-based algorithm compared to alternative ground state preparation for some Hamiltonian. Like, for example, you can go through some tensor network description, try to prepare tensor network state or adiabatic. Because I think here, the main use case is for early fault-tolerant quantum computer, where the error is supposed to be small. So in this case, do we expect in certain cases, this is actually advantageous in actual performance?
Yeah, I think it's a good question, but this is, right, we're probably in year 2 or year 3 for the community to start to be seriously considering these possibilities. I think we have a lot to be learned.
Thanks. Yeah.
All right, so we'll move on to the next talk in the interest of time. So let's thank Lin Lin again.
Thank you.